Japan built a coastal defense system so large that it changed the horizon. Nearly 400 kilometers of seawalls and related barriers. Some sections rise more than 14 meters, higher than a 4-story building. Reported cost: 35 trillion yen, about $7 billion. This was the coast after March 2011. This is the coast today. In some towns, people who once saw the Pacific from their windows now see a solid line of concrete. But here is the contradiction. Japan did not build these walls with the promise that the largest tsunami would never cross them. Engineers know an extreme wave can still rise above the crest. So why spend nearly $13 billion on a defense that cannot guarantee the ocean stays out? Because the real lesson of 2011 was not simply that Japan's old walls were too low. Many failed from the side nobody was watching. Water crossed the top, raced down the landward face, tore away the soil behind the structure, and removed the support holding the concrete up. Then two very different places complicated the story. At Kamaishi, an enormous offshore breakwater was destroyed, but it still weakened the tsunami and delayed its arrival. At Fudai, a 15.5-meter floodgate remained standing and protected a village of roughly 3,000 people. One structure failed and still helped. Another survived and protected a community. That contradiction became the foundation of Japan's new strategy. Do not rely on a wall that claims it can defeat the biggest wave. Build a system that can slow the water, resist sudden collapse, and leave people more time to escape. To understand how Japan reached that decision, we have to return to the afternoon when one of the most heavily defended coastlines on Earth was overwhelmed. Before the water, long before 2011, the Sanriku coast had been shaped by repeated tsunami disasters. Narrow bays, steep valleys, and low coastal plains create natural harbors, but they can also concentrate incoming water. A wave that spreads across an open coast may rise dramatically when it enters a narrowing inlet. Communities responded over generations. They built seawalls, coastal dikes, river gates, and offshore breakwaters. Warning sirens, evacuation maps, and drills became part of daily life. Japan had not ignored the risk. It had studied it, mapped it, and covered parts of the coastline in concrete. But every defense depended on assumptions. How often a tsunami might occur, how high it might rise, and which route it might take. At 2:46 p.m. on the 11th of March 2011, those assumptions collapsed. A magnitude 9, 9. One earthquake ruptured, a fault roughly 400 kilometers long. In places near the Japan Trench, the slip exceeded 50 meters. The movement displaced the water above. The tsunami did not reach the coast as one uniform wall. Open beaches, rivers, and narrow bays transformed it different. In parts of Iwate Prefecture, the maximum height approached 40 meters. Elsewhere, lower waves traveled much farther inland across flat ground. There was no single wall height that matched every place. Some barriers were overtopped, some were struck by debris, some were bypassed through rivers and harbor entrances. Others remained visible after the water passed, but had lost the ground beneath them. Across Iwate, Miyagi, and Fukushima, around 190 kilometers of approximately 300 kilometers of coastal dikes and revetments were damaged. Japan had spent decades preparing. The defenses still failed. Was this bad engineering? Or had Japan asked concrete to stop an event that no practical wall could fully contain? The wrong side. Most people imagine a tsunami pushing against the front of a seawall until the structure falls back. In many locations during 2011, the more destructive process began after the wall had resisted the first impact. Water crossed the crest and accelerated down the landward slope. At the base, the flow began cutting into soil and foundation material. A scour hole formed. Protective blocks lost support. Joints opened. The compacted fill became exposed. As more material disappeared, the structure could slide, rotate, or collapse. The ocean did not always break the concrete from the front. It removed the ground that made the concrete useful from behind. That discovery changed coastal design. The face turned toward the sea still had to resist pressure, salt water, and debris. But the face turned toward the town could determine whether the wall survived overtop. The rear slope needed stronger protection. The landward toe needed more resistance to scour. The crown had to remain connected when water crossed. A standing wall and a breached wall do not produce the same flood. A standing barrier continues to reduce speed and redirect part of the flow. A complete breach becomes an open path into the community. That difference may last only minutes during evacuation. Minutes are the entire point, not one wall. After the disaster, Japan began one of the largest coastal reconstruction programs in modern history. From the air, the result can look like one continuous gray barrier. It is not. The figure of nearly 400 kilometers combines many separate structures across different prefectures. Concrete seawalls, earth-filled dikes, river gates, harbor barriers, offshore breakwaters, raised roads and new housing built on higher ground. By March 2022, coastal work had been planned at 621 locations across 6 disaster-affected prefectures, and 590 projects had been completed. That means hundreds of coastlines and hundreds of local decisions about what should be protected, how high the barrier should rise, and what could not be solved by concrete alone. Even within the same region, dimensions change. Around Kamaishi, some completed walls are about 1 meters high. Other locations use barriers around 5 meters, while some reconstructed sections elsewhere rise above 14 meters. That variation is not a flaw. It is the design. A wall facing the open Pacific cannot be identical to one deep inside a sheltered bay. A narrow valley may be controlled by a flood. A broad plain cannot. A fishing harbor must remain open to boats. Rivers, roads, and people still need crossings. The phrase Japan's 400-kilometer wall creates one simple image. The real project was hundreds of different answers to the same threat. Buried first. The visible concrete is only the final layer. Before a wall rises, engineers have to determine what will hold it from below. One section may stand on dense sand. The next may cross soft river sediment. Another may sit on reclaimed harbor land or connect directly into coastal rock. Soft soil can compress for years. Loose, saturated ground can lose strength during an earthquake. Reclaimed land may settle unevenly. That is why construction begins with boreholes, surveys, and soil tests. Where the ground is weak, engineers may improve or replace it, spread the load across a wider embankment, or transfer forces into stronger material below. Harbor and offshore structures may begin with underwater rock mounds, piles, or large foundations placed before anything appears above sea level. Once the foundation is ready, the dike rises in controlled layers. Soil is compacted and tested. Drainage routes are installed. Concrete armor protects the surfaces. The crown joins the slopes, while toe protection secures the base. From a distance, the result looks like one solid object. In reality, it is a system. The foundation carries the load. The soil provides mass. The concrete resists erosion. The drainage controls water inside the structure. A wall can rise 14 meters above the coast and still fail because of movement that begins underground. The first question is not how high Japan can build. It is what the wall is standing on. Built to be overtopped. The most important change after 2011 was not a new material. It was a new definition of success. Japan divided tsunami planning into 2 broad levels. Level 1 represents relatively frequent events that can still cause serious damage. For these tsunamis, seawalls, dikes, and breakwaters are expected to prevent or greatly reduce inland flooding. The wall is the primary defense. Keep the water out. Protect homes, roads, and ports. Level 2 represents an extreme, low-probability disaster on the scale of the largest credible tsunami. For that event, relying on wall height alone is not realistic. The structure becomes one layer in a larger system. It should resist complete collapse, reduce the force of the water, and delay its movement inland. Warning systems, evacuation routes, vertical shelters, raised roads, land use planning, and relocation must do the rest. This is why the new barriers are designed to remain useful even when a wave exceeds their height. That sounds like a wall built to lose. But overtopping is not the same as immediate failure. A barrier that remains standing for several extra minutes may keep one road usable longer or allow more people to reach higher ground. People do not evacuate in engineering diagrams. They evacuate minute by minute through traffic, rain, debris, and uncertainty. The wall does not have to defeat the largest tsunami to save lives. It has to remain useful while it is being overwhelmed. Would you trust a structure more if engineers promised it could stop anything? Or if they admitted its limits and designed the town around what happens when those limits are exceeded? The openings, no coastal defense, can be completely sealed. The places that must remain open are also the places water can exploit. A seawall may block the direct path from the ocean, but a tsunami can enter a river mouth and travel upstream. That means river levees, Floodgates and seawalls must operate as one net, but a river gate creates its own contradiction. It must remain open during normal conditions so water can flow and boats can move. When a tsunami approaches, it must close quick. The earthquake may already have damaged power, roads, or mechanical equipment. Automation removes workers from danger. Automation can also fail. Manual operation gives people control, but sending someone toward the sea after a major earthquake can turn a mechanical problem into a human tragedy. During the 2011 tsunami, some gates remained open because equipment failed, power was lost, or operators could not reach them in time. Fishing harbors create another gap. Seal them completely, and the wall damages the economy it protects. Leave them open, and the town needs gates, breakwaters, or multiple defensive layers. The wall protects the community by separating it from the sea. The community survives by remaining connected to the sea. Engineering has to do both. Two lessons, Kamaishi and Fudai, became two of the most important examples because they produced opposite-looking outcomes. At Kamaishi, engineers had built what was then recognized as the world's deepest breakwater. Its foundations reached water about 63 meters deep at the entrance to the bay. It had taken decades and cost around 120 billion yen. The 2011 tsunami destroyed large sections of it. From the surface, the conclusion seemed simple. A colossal investment had failed. But later analysis showed that the structure had reduced the tsunami height inside the bay and delayed its arrival by about 6 minutes. It did not save Kamaishi from devastation. It did not remain intact. But before it failed, it changed the way. 6 minutes can mean another road reached, another staircase climbed, or another group moved toward higher ground. Can a structure be called successful if it is destroyed? Kamaishi suggests that performance may be measured by what a structure changes before it fails. Fudai offered the opposite image. The village sits where steep terrain narrows the path from the sea. After earlier disasters, local leaders supported an unusually high floodgate. Completed in 1984, it stood 5 meters tall and was criticized as excessive for a small community. In 2011, the gate protected the central village and roughly 3,000 residents. Fudai is often presented as proof that Japan should simply build higher, but geography was part of its success. The narrow valley allowed one barrier to control a concentrated route. Place the same gate on a wide plain and water could move around. Kamaishi broke and still bought time. Fudai stood and protected a village. Neither provides a universal design. Together, they explain why Japan rebuilt hundreds of different defenses instead of copying one wall along the entire coast. Safer or blind? For an engineer, a seawall is measured in height, pressure, and stability. For residents, it is also measured by what disappears behind it: the view, the wind, the sound of the water. Along parts of northeastern Japan, people who once saw the Pacific now live behind concrete several stories high. Supporters see protection for towns, ports, roads, farms, and industrial. Even if a wave exceeds the crest, the wall may slow flooding and provide more evacuation. Critics see a coastline cut off from itself. Some communities were relocated to higher ground, leaving large barriers in front of areas with fewer homes than before. Fishing, tourism, and local identity depend on an accessible shoreline. Environmental concerns include changes to beaches, rivers, and coastal ecosystems. There is also a psychological risk. A massive wall creates confidence. Confidence can become delayed. Residents may assume the structure will hold and wait instead of evacuating immediately after strong shake. A wall designed to buy time could persuade people to waste, but removing the walls creates another danger. A moderate tsunami that could have been contained may again reach roads, ports, and low-lying businesses. This is not a choice between perfect safety and a beautiful natural coast. It is a choice between physical, economic, environmental, and psychological risks. The wall may make a coastal town safer by separating it from the ocean. But how much separation can a coastal town survive? Time. Not victory. Japan did not rebuild the coast with concrete alone. Some neighborhoods moved uphill. Some low areas were raised. Roads became secondary embankments. Evacuation stairways were added to hills, schools, and elevated infrastructure. Warning networks were expanded. At many locations, plans changed as communities debated wall height, alignment, relocation, and land use. The final defense is therefore not one object. It is a sequence. The earthquake begins offshore. Sensors detect the movement. Warnings start the clock. Floodgates close where possible. Breakwaters alter the way. Seawalls hold back smaller events and slow larger ones. Raised roads create another obstacle. Evacuation routes move people away from low ground. Vertical shelters provide refuge where hills are too far away. Concrete is one layer. Against a smaller tsunami, the wall may keep the water. Against a larger event, it may reduce depth and delay flooding. Against the largest credible wave, it may be overtopped and damaged. But every extra minute still matters. That is why the title of this project is also its contradiction. Japan built nearly 400 kilometers of tsunami walls, but not to stop the biggest wave. Not completely, not everywhere, and not forever. It built them to control the events that can be controlled, weaken the events that cannot, and prevent sudden collapse from turning a disaster into something even worse. Looking back from the ruins of March 2011 to the reconstructed coastline today, these walls represent more than concrete. They represent a country trying to convert loss into design. Every section contains an argument about how much protection is enough, how much separation a community can accept, and how much trust should ever be placed in a structure facing the ocean. The people who rebuilt these coasts will eventually disappear into history. The disputes over height, cost, and appearance may fade. Yet the walls, gates, raised roads, and evacuation routes will remain as evidence of the choices made after one of Japan's darkest days. Future generations may look at them and see protection. Others may see a coastline hidden behind concrete. Both views can be true. That is the real legacy of Japan's tsunami defenses. They are neither an invincible shield nor a meaningless monument. They are a compromise between engineering and uncertainty, between living beside the sea and preparing to run, between the belief that nature can be controlled and the knowledge that it never can be complete. The walls may one day be overtopped. Some may be damaged. Some may eventually fail. But their value will not be measured only by whether every block remains in place after the water arrives. It will be measured by what happened before the collapse. How much energy was removed? How long did the barrier remain standing? How many routes stayed open? How many people reached higher ground? Because when the tsunami rises above every wall, survival is no longer measured in meters of concrete. It is measured in minutes, and the wall's final job is to leave some of those minutes behind. If this documentary changed the way you see Japan's tsunami walls, tell us in the comments. Would you choose a higher wall, a clearer view of the sea, or a combination of both? Like and share this video to support the channel. Subscribe and turn on notifications so you do not miss the next extraordinary engineering project we explore.